In this example, we are asked to find the limit as x approaches 0 from the right of the function 1 plus x all raised to the cotangent x power. To evaluate this limit, we're going to run into a problem if we were to directly sub the 0 in. If we were to directly sub the 0 into the cotangent x and the exponent, we would get cosine of x over sine of x. I'm simplifying the cotangent. And if you put the 0 into that, you would obviously get 1 over 0. We cannot divide by 0. So that raises a problem. Now, since we have an exponent here, what we can do is we can rewrite this in a form that will give us an indeterminate form when we substitute the 0. That is the ultimate goal, because what we want to do is use L'Hopital's rule, which is what this lesson is about, to evaluate the limit, even though it will give us an indeterminate form. So what we're going to do is, because we have this cotangent here and the exponent, we can use the rules of logarithms to bring that down. But before we do that, we want to assign this all to a variable, the entire expression. So if we set y equal to the limit as x approaches 0 from the right of 1 plus x to the cotangent x, we now have a form that we can work with. So what we're going to do is we're going to take the natural log of both sides, and you will see why in a moment. So the ln of y equals the limit as x approaches 0 from the right of cotangent x times the ln of 1 plus x. The significance of this is that now that we have this form, we'd still have that problem if we substituted the 0 in, but now we can actually move the cotangent to the bottom by dividing by 1 over cotangent. So, if we rewrite this, the limit as x approaches 0 from the right of now the ln, it's supposed to be 1 plus x, all over, and 1 over cotangent is the same as tangent, tan x. At this point, if we substituted the 0 in, we would get an indeterminate form. We would get 0 over 0. Let's check that. If you put the 0 into the numerator, we're going to get the ln of 1 plus 0, which is 1. The ln of 1 is 0. So that's how this becomes a 0. And plugging in a 0 into tangent x, which is the same as sine over cosine, the sine of 0 is 0, over the cosine of 0 is 1, which gives us a 1. 0 over 1 is 0. So that's how we get our indeterminate form here. So now that we have this indeterminate form, we can use L'Hopital's rule to evaluate the limit. And essentially what L'Hopital's rule is, and we'll go over here, if you have an expression f of x over g of x, and the limit of this, for an example, x approaches a, if this goes to an indeterminate form, such as 0 over 0, we can actually evaluate the limit by taking the derivative of the top, so x prime of x, f prime of x, over the derivative of the bottom, g prime of x. What you do not want to do is use the quotient rule, because you're not taking the derivative of the expression itself, you're only taking the derivative of the numerator and the derivative of the denominator separately, as if they were their own expressions. So, if we go back to the original example, what we want to do now is take the derivative of the top and take the derivative of the bottom, because we got the indeterminate form. And it should be noted, excuse me, it should be noted that using the natural log technique here, where I took the natural log of both sides, is only useful when you have an exponent expression. So, what we want to do now, if we have the ln of y equals the limit as x approaches 0 from the right of now the derivative of the top and bottom, that's going to give us 1 over 1 plus x times the derivative of 1 plus x, which is just 1. All of that over the derivative of tan x, which is going to give us secant squared x. And now, at this point, we can do a direct sub. So, what we're going to get now is the ln of y equals the limit as x approaches 0 from the right of this 1 over 1 plus 0 times 1 over secant squared of 0. So, the numerator is going to give us 1, because 1 over 1 times 1 obviously is 1. And the denominator, secant squared, I will simplify that into 1 over cosine squared. And now that we have the 1 over cosine squared, it's easier to figure out what that value is. If we substitute a 0 into that, we're going to get a 1 over 1. Cosine of 0 is 1, squared is 1. So we get a 1 over 1 over here. And at this point, we only have one step left. This is a very important thing to remember. It is very crucial that you write out the ln of y in front of the entire expression before the equal sign every time you do each step, because it's very easy to forget to go back and reverse the natural log function. Because it's not so much that y equals this. This is saying the natural log of y is equal to this expression. So what we want to do now is put it into the exponential form. So y equals the limit as x approaches 0 from the right of, and we had, well, we found out this was equal to 1. But since we're doing the exponential form, this is going to be e to the 1 power, just bringing the 1 above the e, which was our answer. The 1 was the answer. And that's how we get our final answer. Y equals e to the first power, which is just e. So, to make that a little clear, again, very crucial, once we have the natural log of y equals this expression, which was evaluated to 1, we have to rewrite that so that we get rid of the natural log function, which is where I got the e, and we bring whatever that value was to the exponent of the e. And that is our final answer, right there.